Today I am here to discuss about the acid-base titration. Myself, Ms. Krishnapriya KR, Assistant Professor, Department of Pharmaceutical Chemistry, Yenepoya Pharmacy College and Research Center. These are the table of contents: introduction, theories of acid-base titration, relative strength of acid and bases, acid-base indicators, neutralization curves and references. These are specific learning outcomes. At the end of the lecture, students should understand the different acid-base theories, compare the acid and base strength and choose the correct acid-base indicators and interpret the neutralization curve. The acid and bases are the two important classes of chemical substances. These are mainly recognized based upon the taste. The taste, the acid that having the sour taste and the pH is less than 7 and changes the phenolphthalein from red to colorless. And the base that is a bitter taste and pH is greater than 7 and turn the red litmus paper into blue, and the phenolphthalein is changing from colorless to pink. The neutralization is a process. The acid and bases react with each other to produce an ionic substance is called salt. The process is known as neutralization. These are the theories of acid-base titration. In 1777, Lavoisier proposed that oxygen was an essential element in acid, and after that 1808, the Humphrey Davy, he suggested that hydrogen chloride dissolves in water to give hydrogen and chlorine. After that, three concepts arrived. These Arrhenius concept of acid and bases, Bronsted-Lowry concept and Lewis-base concept. This Arrhenius concept of acid bases, the acid is a substance which yield hydrogen ion H+, these ions in aqueous medium, and the HCl is dissociated to get H++ and Cl-. The base is a substance which yield hydroxy ion in aqueous medium, that is NaOH is dissociated to get Na++ OH-. These are the main limitations of Arrhenius concept. The free H+ and OH- ion do not exist in water because this H+ ion is reacted with water to form hydronium ions. Next limitation is limited to water only. This Arrhenius only discuss about the action on water. Other solvents is not mentioned. Some bases do not containing OH-. That means the bases like ammonia, calcium oxide that do not containing any OH- ions. It cannot explain the acidic characters of certain salts such as AlCl3 in aqueous solution. The Bronsted-Lowry concept in 1923, the Johannes N. Bronsted and Thomas M. Lowry defined acid and bases in terms of proton transfer. The acid is a proton donor and base is a proton acceptor. As per Bronsted-Lowry theory, the acid that dissociated to get H+ and conjugated base. For example, HCl is dissociated to get H++ Cl- and is acetic acid like CH3COH and dissociated to get H++ CH3CO-. In case of base, the OH that accept the H+ and forming water, and ammonia that is accepting the H+ and to form NH4+, this is conjugated acid. The conjugated base is an ion or molecule is left after the acidic acid donates a proton, and conjugated base is an ion is formed after the accepting a proton. The main limitation of Bronsted-Lowry theory is substance like BF3 and aluminum chloride do not have any hydrogen, hence it cannot give a proton but it always behaves as acid. Next is Lewis concept of acid and bases. In 1923, G.N. Lewis is proposed the definition of acid and bases in terms of electronic structure. The Lewis acid is a molecule or ion that can be accept a lone pair of electron, and Lewis base is a molecule or ion that donate a lone pair of electron. Here A is a Lewis acid, B is a Lewis base. The A accepting the lone pair of electron and forming a AB complex. These are the limitations of Lewis base concept, and is a relative strength of acid and bases cannot explain by this method. Then relative strength of acid and bases. The stronger acid are those that loses the protons more easily than others. Similarly, the stronger bases are those that hold on to proton more strongly than others. The relative strength of acid. The strength of acid is mainly depend upon the ability to transfer its proton to the base and form a conjugated base. Here Ha is the acid and reacted with water to get H3O+ is hydronium ions and plus a conjugated base. Here H3O+ is equal to H+, then the equation is converted to Ha plus water to give H plus plus A minus. Here we are applying the law of mass action. The dissociation constant of acid is equal to concentration of H plus plus concentration of A minus divided by concentration of Ha. Next is relative strength of bases. According to Arrhenius concept, a base is a substance which produces OH minus ion in aqueous solution, and BOH is dissociated to get B plus plus OH minus, and applying the law of mass action, the dissociation constant of base is equal to concentration of B plus plus concentration of OH divided by concentration of BOH. The acid base indicator. These indicators are mainly used in the neutralization titration are called acid base indicator or hydrogen ion indicators or pH indicator, and these they are changes the color within a certain pH range, and the endpoint of this titration is called as equivalence point. The indicators are methyl orange, phenolphthalein and methyl red. The methyl orange, the pH range of 3.2 to 4.5, and the color changes from orange to red, and the phenolphthalein in the pH range of 8.3 to 10.5 and the colorless to pink. The methyl red is 4.4 to 6.5 and the color changes from red to yellow. Next is the characteristics of good indicator. The color must be easily detected, and the color change must be rapid and sharp, and the indicator molecules must not react to the substance being titrated, and the color change by the indicator must indicate the completion of reaction. The indicators are weak acids or bases which have different color in the conjugated base and acid form. This is an unionized form of indicator that dissociated to get H plus plus ion minus, and we are find out in the K indicator is equal to concentration of H plus plus concentration of ion minus divided by concentration of unionized indicator. The color changes when concentration of indicator is equal to concentration of unionized molecule. The indicator changes the color when K indicator is equal to concentration of H plus. When the selection of indicator, the titration of strong acid and strong base, here the indicator with the pK indicator value in between 4 and 0, and the titration of weak acid, the pH of the equivalence point is greater than 7. That indicator is used as phenolphthalein and thymol blue with pK indicator is greater than 7. And the titration of weak base, the pH of the equivalence point is less than 7 and the indicator is used as bromocresol blue. Next is the theories of indicator. Two theories have been proposed to explain the changes of color in acid-base indicators which changes the pH. These are the theory Oswald theory and Quinoid theory. Here Oswald theory is based upon ionization. The color changes the acid-base indicator is a result of its ionization. The indicator showed different color in ionized and unionized state. The color of the indicator is mainly depends upon the proportion of ionized and unionized state of indicator. The acid-base indicator is either a weak acid or weak bases, and ionization is affected by the presence of acid and bases. The indicator is a weak acid, its ionization in acid is very low and fairly well in alkalis. The action of phenolphthalein. Phenolphthalein is a weak organic acid, is denoted as HPH and is almost unionized in acidic medium, and unionized molecules are colorless, and while the ionization it gives pink colored pH minus ion. This is a unionized form is HPH is colorless and dissociated to get H plus plus pH minus. The pH minus is showing pink color. In the presence of an acid, due to the increase in the concentration of hydrogen ion and dissociation of HPH is suppressed and solution become colorless. And the addition of strong bases like NaOH, KOH and the OH minus ions are combined with H plus ions from phenolphthalein, and equilibrium got disturbed and more phenolphthalein is ionized to produce pink colored pH minus ions. The HPH is dissociated to get H plus plus pH minus, and NaOH is dissociated to get OH minus plus Na plus. And the OH minus and H plus is combined to get water, and Na plus and pH minus is combined to get pink color NaPH compound. Next is methyl orange. It is a weak base, is unionized molecule is showing yellow color and does give red colored Me minus ion on ionization. The acid solution of methyl orange is give the red color. The MeOH is dissociated to get Me plus plus OH minus, and HCl it is dissociated to get Cl minus plus H plus. This Me plus and Cl minus is combined to get MeCl and is showing the red color, and H plus and OH minus is combined to get water molecule. These are the indicators. The phenolphthalein is a weak acid and is unionized form is showing colorless and ionized form is showing pink color, and the methyl orange is a weak base and showing yellow color in unionized form and is ionized form showing red color. Next is quinoid theory. The acid base indicators exist in two tautomeric form having different structure. The two forms are in equilibrium, that is benzoid form and quinoid form. These two forms having different color. The color changes is due to the interconversion of this tautomeric form. The quinoid form is usually deeper in color than the benzoid form. One of the tautomeric form exists in acidic solution while other in alkaline solution. Therefore, the pH of the solution is various and color of the indicator is also various due to the interconversion. The action of phenolphthalein. The phenolphthalein, which is a dibasic acid, it possesses benzoid structure in acidic medium and is colorless, and it possesses quinoid structure in alkaline medium, that is give pink color. Then mixed indicator is mainly used when the detection of endpoint is difficult, that is titration of weak acid and weak bases. The ordinary acid base indicator is not possible when mixing with suitable indicator to get the good endpoint. Use of two indicators to obtain the sharp color change. The both indicators selected based upon the K indicator. These are the examples: bromocresol green and methyl orange. The pH range of 4.3 is color changes from orange to blue green, and the bromocresol green and chlorophenol red, the pH of 6.1 and color changes from pale green to blue violet, and bromothymol blue and neutral red, the pH range of 7.2 and the color changes from rose pink to green, and bromothymol blue and phenol red, the pH of 7.5, the yellow to violet color, and bromothymol blue and cresol red, the pH of 8.3, the color changes from yellow to violet, and bromothymol blue phenolphthalein, the pH range of 9 and the color changes from yellow to violet, and thymolphthalein and phenolphthalein in the pH range of 9.9 and colorless to violet. The universal indicators are mixture of pH indicator that changes the color in a wide range of pH range, typically from strong acid to strong base. Next is a neutralization curve. The titration curve is a plot of pH of the analyte solution versus volume of the titrant added to the titration process. Here the curves are useful for determining the endpoint and dissociation of constants of weak acids or bases, and helps in selection of indicator. These are the types of acid-base titration. The titration of strong acid strong base, that is HCl and NaOH. Titration of weak acid strong base, the CH3COH and NaOH. The titration of strong acid weak base, the example is HCl and NH3, and titration of weak acid weak base, that is CH3COH and NH3. Here the strong acid strong base titration. For example, HCl is treated with NaOH and to get NaCl and water. Here the titrant is NaOH and titrate is HCl. We are plotting the pH of the titration curve of the strong acid with strong base. This is a neutralization curve. The point A indicating here the no NaOH is added. Here the pH of the analyte is low. When HCl is reacted with water to get hydronium ion and Cl minus. When NaOH is added dropwise, the H3O plus is slowly started getting consumed by OH minus ions and produced by the dissociation of NaOH. The point B is the pH recorded at the time point just before completing the neutralization takes place. The point C is the equivalence point. Here the moles of NaOH is added is equal to moles of HCl in the analyte. The H3O plus ions is completely neutralized by the OH minus ion, and the pH is neutral. Neutral means pH is equal to 7, and the point T is after the equivalence point. The NaOH is still added from the burette, hence now excess of OH minus is present in the pH and the pH is become basic. Next is the titration of weak acid and strong base. Here the weak acid is CH3COH plus NaOH to get CH3CONa plus water. The point A indicating here no NaOH is added yet, the pH of the analyte is low and H3O plus is present. The acetic acid is a weak acid, the starting pH is higher than HCl. The point B is the pH recorded at the time just before completing the neutralization takes place, and the point C is the equivalence point. The moles of NaOH added is equal to moles of CH3COH in the analyte, and the point D is beyond the equivalence point. The curve is identical to HCl NaOH titration curve. Then the titration of strong acids, weak base. Here the strong acid HCl is reacted with water to form H3O plus Cl minus. The H3O plus is reacted with NH3 to get NH4 plus water. The NH4 plus is conjugated acid. The point A, there is no NH3 is added, so the pH of the analyte is low. The point B is the pH is recorded at the time point just before completing the neutralization takes place. And the point C is the equivalence point, that is moles of NH3 added is equal to moles of HCl in the analyte of the pH. The pH is not neutral, it is acidic because NH3 plus is forming, that is conjugated acid. The point D, after the equivalence point, the NH3 is continuously adding in excess and the pH is increases because NH3 is a weak base, so the pH is above 7. Then the titration of weak acid, weak base. Here the weak acid CH3COH reacted with NH4OH to get CH3CONH4 plus water, and the weak acid is partially dissociated and neutralized with the NH4OH, which is the weak base, is showing a continuous decrease in the pH and pH changes is not observed properly. This is a summary of the section. The different theories, Arrhenius, Bronsted and Lowry and Lewis is explained the acid and base's behavior in chemical reaction, use of these values like pKa, pKb to identify how strong or weak the acid or bases and how they affect the titration result. And the indicator helps detect the endpoint of titration by changing the color at a specific pH range, analyzes the titration graph to find the equivalence point, understand the pH change and also choose the right indicator. These are the references, and thank you.